This is our 6 degrees of freedom robot arm, and it took us 2 years to get here. 2 years of trial and error, problem solving, and plenty of moments where we questioned why we even decided to build it. We built everything from scratch. We 3D printed the entire body, designed all the custom electronics, and wrote over 5,000 lines of code. But to understand how we got here and why we made the choices we did, let's go back to where we left off in 2023. The shaft for joint 3 snapped. The problem was that we used this L-series timing belt. These belts are designed for metal machines, so they need a lot of tension to work properly. But in our case, that tension was being applied to a 3D printed shaft, which simply wasn't strong enough, so it broke. Instead of trying to get the belt system to work, we are going for a much simpler solution. We will mount the motor directly at joint 3. Joint 2 has a high enough gear reduction to support this additional torque, so it shouldn't be a problem. Another change we want to make is to home joint 2 and 3 using inductive proximity sensors. These sensors produce a voltage signal when metal is detected, so we can use them for contactless homing of the joints. With this new plan, we spent the next few days redesigning the parts, printing everything, wiring up the motor, and reassembling the arm. Piece by piece, it started to come back together, this time with the mistakes from V1 fixed. At this point, we could just cover up the robots and call it a wrap. But after finishing our co-op in mid-2024, we came back with a bunch of new skills, so we knew we had to implement them. Before jumping into the improvements, let's talk about an area we haven't really gone deep into yet, the electronics. For the main controller, we've actually been through 2 iterations. The first was a Teensy 4.1 on a perf board, with connectors for stepper motor signals and limit switches. It worked, but the setup was a bit fragile. So for the second version, we designed a custom PCB around the ESP32. We switched to an ESP32 because we were burning through Teensy boards, and at nearly $40 each, the cost adds up. Even though the ESP32 is a little slower, it is much cheaper and more than capable of handling the motion control for this robot. We also added optocouplers for the proximity sensors and gave each switch its own dedicated connector. This made assembly much easier. Now for driving the stepper motors, we used the MKS Sable 42C drivers for the NEMA 17s and the 57Cs for the NEMA 23s. They used a simple step and direction interface. The controller sends pulses on one pin to tell the motor when to move, and the other pin sets the direction. So how can we make this robot better? Our biggest issue right now is wiring. Each motor has 4 signal wires, 2 for step and direction, and the other 2 for the limit switches. If you factor in the power lines for each motor, that's about 32 wires running through the arm, and that's way too much. So to fix this, we are going to be switching to a bus architecture, specifically the CAN bus. In a bus architecture, instead of having dedicated wires from the controller to each motor, all the motors share the same communication line, kind of like how multiple houses on the street share the same road. This means that we only need 2 wires for the CAN bus itself, plus 2 for power. That's just 4 wires, instead of the 32 we currently have. But the benefits go beyond just reducing the number of cables we are using. With our current setup, the controller does all the heavy lifting. It is responsible for planning the overall path and also generating every single step pulse for each motor. With a CAN bus, we can give each motor its own dedicated controller. So the main controller just sends high-level commands like move to this position at this velocity, and each motor controller handles the actual motion planning on its own. This approach is called a distributed control system. We are spreading out the processing load across multiple boards, instead of letting one controller handle everything. Now, could we just buy off-the-shelf CAN motor controllers? Yes, we definitely can, but where's the fun in that? We want to design everything ourselves, so we have full control of the algorithms running on all parts of our robot. This means we need to select all the components, so let's talk about the parts we are going with. Let's start with the brain of the operation, the main robot controller. We need a microcontroller that is fast, reliable and packed with all the hardware features we need. With this in mind, we are going with the STM32H7R7, and there are some really compelling reasons why. First off, this chip is fast. It runs at 600 MHz, which is the same clock speed as the TNC 4.1. It also has an FPU, or a floating point unit. It is basically specialized hardware that makes math operations on decimal numbers very fast. This is going to be crucial for our path planning and inverse kinematics algorithms. On top of that, it has an LTDC, a hardware controller specifically designed for driving LCD displays. We are planning to add a touchscreen to it, so having dedicated hardware for this is going to come in really handy. Now, it's not all perfect. This chip only has 64 KB of internal flash, nowhere near enough to store all of our application code. So to solve this, we are adding this external 8 MB flash. There's also a RAM situation. With only 600 KB of internal RAM, we fall short of what's needed for our LCD frame buffer. If you don't know what a frame buffer is, it is basically the memory space that stores the pixel data for the display. With our 800 by 480 pixel screen at 24 bits per pixel, we need about 1.2 MB just for one frame buffer. And since we want to double buffer, we actually need double that, so we are using this 8 MB SD RAM to handle the frame buffer storage. Beyond the microcontroller, we are adding a CAN transceiver to handle the differential CAN signals, a USB to UART converter for serial communication, status LEDs, and an optocoupler for an emergency stop circuit. Now let's move on to the stepper motor controllers. We are using the STM32G431 as the microcontroller for all the drivers. It runs at 170 MHz, which is more than fast enough for our motion planning algorithms. For actually driving the motors, we are using trinamic chips. For the NEMA 17, we went with the TMC2209. This chip has all the MOSFETs built right in, so it saves a ton of board space. But there's a trade-off. It maxes out at 2 amps. So for the NEMA 23 motors, which are rated for 3 amps, we are using the TMC5160. This chip doesn't have internal MOSFETs, so we have to add our own external ones. We selected these N-channel MOSFETs in the SOT23 package. I ran the thermal calculations, and they should be able to handle our current requirements without overheating. We are also adding magnetic encoders for possible closed-loop control later, and each board includes RGB LEDs for status indication and circuitry for the proximity sensors. Now that we have selected the components, it's time to design the PCBs. I have actually designed a NEMA 17 stepper motor driver before, but there were a lot of mistakes, so I'm going to fix them in this next revision. After a few weeks of designing, I sent the boards out to our sponsor, GLC PCB, for fabrication. GLC PCB provides PCB manufacturing and assembly services for both hobbyists and professionals. We've actually been using their services long before we started this YouTube channel, so when they reached out to sponsor us, it felt like a natural fit. The reason why we've been using their services for so long is because they are super affordable. You can get 1 to 8 layer boards for only $2, and it is also very easy to place orders for your PCBs. All you have to do is just upload your Gerber files, select the options you need, get an instant quote and place your order. They handle everything in-house, so you get consistent quality and reliable turnaround times. They currently have a 6-layer PCB special promo, where you get $30 off with free in-ink finish and VI pad. We have links down in the description if you want to check them out. After a week, the PCBs arrived and they look fantastic. Now it's time to assemble the boards. With the PCBs assembled, we can begin testing. I put together a checklist to test all the different peripherals on the boards. Fortunately, most of the tests passed. CAN communication is working, serial communication is also working, and the other circuitry checks out. However, I ran into an issue with the LCD screen. I am trying to display an image, but we can barely make out what it is. After a lot of debugging, I found that the LTDC FIFO underrun flag was set. This means the LTDC can't retrieve pixel data from the memory fast enough. I did some research, and it looks like the PCB layouts could be the issue, so I'll fix it in the next revision. On the NEMA 23 driver board, I've got the positions for the screw holes wrong, so those need to be fixed. I also added a heatsink mostly for aesthetic reasons, but after thinking about it, I'm going to switch from the SOT23 package to a TDSON package. Even though I haven't had any thermal issues with the SOT23s, the new MOSFET should handle heat much better. There are no issues with the NEMA 17 drivers, but since I'm ordering new PCBs anyway, I want to move a few components around and improve the layout. While redesigning the main controller, I came across a HyperRAM. It's a type of high-speed external RAM that uses 8 data lines, runs at 200 MHz and uses double transfer rates, meaning that it transfers data on both edges of the clock. That gives us up to 400 megabits per second of theoretical bandwidth, more than enough for our LCD, so we are going to be using that instead. After finalizing the redesign and shrinking the overall board size, I sent the boards out for fabrication, and about a week later, the boards arrived. For this batch, I decided to go with the ink finish because of the golden solder parts. I also went with the black solder masks for the motor drivers instead of the traditional green. And honestly, I'm so happy with that decision because the PCBs turned out really well. Now it's time to test the new revision. Of course, because this is hardware development, nothing ever goes smoothly the first time. The first issue was entirely my fault. I placed the EEPROM in the wrong orientation, which immediately shorted the 3.3 volts rail. Thankfully, no components were damaged, and after removing the EEPROM, everything worked fine. The second issue was with the HyperRAM. I couldn't get it to display an image when running the clock speed above 150 MHz. I initially thought this was a PCB issue again, but it was actually firmware this time. The GPL pins connected to the HyperRAM runs at a lower voltage of 1.8 volts, so the HSLV option byte is needed to be set to optimize the pins for this voltage. Setting this byte allowed me to hit the 200 MHz limit. The image is now perfect, but I found something interesting. The MCU doesn't allow best reads to cross a 1 KB boundary. When this happens, it automatically breaks the transfer into single accesses, which are much slower. So to prevent this from happening, we need to make sure the frame buffer is not placed at the edge of a 1 KB boundary. We can do this by adding dummy bytes to the end of each line to make sure they are multiple of the best size, 128 bytes. Looking back, I think this fix would have worked for the SDRAM as well. But at this point, we are far into the HyperRAM development to turn back. Just when I thought we were in the clear, we hit a major roadblock. The serial communication wasn't working. This wasn't supposed to be an issue because I basically copied and pasted a schematic from the initial revision. But it turns out I accidentally swapped the USB data lines. I think this happened because I modified the USB connector symbol for V3, but then accidentally updated it from the library whilst working on this revision, and so it overwrote all my changes. Fortunately, I added a UART connector as a backup. However, I managed to short the board whilst connecting the wires to it, so we are going to be using V3 for development. This means we won't be able to work on the GUI just yet, but that's fine. We are going to start by writing the firmware for the core functionality of the robot. Now let's move on to the most complex part of this project, the firmware. Back when we were using the TC and the ESP32, we could rely on Arduino libraries to handle things like the stepper motor control and the communication protocols. But moving to the STM32 means implementing all of that ourselves, so we've got a lot of work ahead of us. While writing the firmware, I tried using Claude to review my existing code. It suggested things like using function pointers for cleaner state transitions and better ways to handle the error. It helped me improve my code pretty quickly. I wouldn't trust it to write everything from scratch, but it's great for brainstorming approaches and catching silly mistakes. Think of it as a second set of eyes. Not perfect, but very useful. After writing over 5,000 lines of code, we are finally ready to put this thing to the test. I built a custom serial interface that allows me to send commands to the robot directly from my laptop. This way, I can quickly tweak the parameters. First up, I'm testing the configuration settings like the motor current and microstepping. Without working, now let's test the actual movement. I need to verify that the motor moves to the correct positions and that I can adjust the speed. Everything's perfectly working on this single motor. That means it's time to go all in. Let's assemble the remaining motor drivers and run a full test. With everything connected, now comes the most nerve-wracking moment, turning it on for the first time. Oh! It feels good to switch on the power and nothing blows up. I wrote a test sequence that cycles through all the motors and tests every function. So let's run it and see if this thing actually works as a complete system. With the electronics out of the way, let's talk about the mechanical redesign. We kept the overall design philosophy from V2, but we made several key improvements. First and foremost, we shrunk the first segment of the arm. In V2, the arm was a little too long, so we just made it slightly smaller in this revision. We also upgraded the base with a tapered roller bearing to support the main shaft. We are having stability issues with the base wobbling under load, so this should make it much more rigid. We also added bearings to adjust the tensions in the belts at joints 1 and 5. This change should hopefully keep the belts tensioned. Let's move on to wiring because here's where the CAN bus really pays off. Since we've dramatically reduced the number of wires running through the robots, we can hide them now. We are creating channels through the shafts so we can pass cables internally between joints. This means the wires from joint 3 to 4 and from joints 4 to 5 will completely be invisible from the outside. It's going to look much cleaner. With this design planned out, let's get to building. Before we do anything else, we need to move each joint one at a time. This lets us verify the default motor directions so that we are sure the motor moves to the intended position when commanded. As soon as we tried this, the power supply completely gave up on us. We were drawing way more current than it could handle, so we had to order a more powerful one. A few days later, the new power supply arrived, so we swapped out the old one, and with power finally sorted, we can move forward. The next step is homing. Homing uses proximity sensors or limit switches to find a reference point, so the motor knows its exact position every time you power it up. And immediately, we hit another wall. The proximity sensor on joint 2 was faulty. It was always outputting a signal. That meant that the joint thought it was already at home, so it couldn't home properly. We had to take the robot apart and replace the sensor. After replacing the sensor, we can now home the robot. With that done, we can finally close it up and move on to the real magic: inverse kinematics. Inverse kinematics is basically the math that finds the joint angles needed to place the end effector at a desired position and orientation. I've already done the math for this and written the code, so let's test it. And it mostly works. The robot reaches the right position, but the orientation is completely off. The reason for this was that I forgot a minus sign. With that fixed, the robot is finally ready. So now let's see it move to a few random positions. The robot is finally done, but there's still a lot more we can do. We still have a touchscreen to add, and we can develop better motion control algorithms. Consider subscribing if you are interested in following along on our journey. Thanks for watching.